Well, you guys have been working hard this module at bringing calculus into applied geometric situations, right? So we started with two-dimensional. We worked with area and perimeter, and then we brought geometry, and that was geometry. We brought calculus into it with the words like maximize and minimize. Then we went 3D, and we talked about volume and surface area. Now we're going to go into some additional geometry topics, but also some topics in business and economics, like profit. So calculus can be applied to all these other topics just by throwing in the word maximum or minimum, and that is what's called optimization, and that's where calculus comes in. So today we're going to talk about distance, talk about profit, but all of this stuff is the same. Critical points, identify and interpret, go back and make sure you answer the question. All right, so let's start with an algebraic topic. Find two numbers whose sum is 6 and the sum of the squares is a minimum. Okay, so we know we're talking calculus here because we have the word minimum. What we're trying to find are two numbers. So let's talk about the first number, which we'll call x. So that'll be number 1. And the second number, which we're going to call y, so that'll be number 2. And we know that the sum is 6. That means x plus y equals 6. We also know the sum of the squares is a minimum. So the sum of their squares, so it's still a sum, and we're squaring them, x squared and y squared, and we don't know what that is, but it's going to be a minimum. We still are doing the same algebraic idea. You find a variable that looks like it's the easiest to get alone, and so I would say, oh, let's get this y by itself here. So if I get y alone, y is going to be equal to 6 minus x. Then I'm going to take that and I'm going to substitute into the other equation in place of y. So I'll have x squared plus parentheses 6 minus x, quantity squared, and that's still equal to I don't know. But now I'm ready to do the calculus part of it. I'm ready to find out when the sum of these squares would be a minimum. And so the minimum means I'm going to find the calculus derivative and look for the critical point where it would be a minimum. So now I'm ready to do a Math 8 on this equation. All right, we're setting up our window for this. Now our window here, the sum of these numbers is 6, which means that these numbers aren't very big, they're small. And so I can for sure get away with 0 to 10 on my window. And I'm going to see my graph coming through here, and so I'm going to identify that critical point as my minimum, which turns out to be 3. And so I now know that my first number is the number 3, but it says find two numbers. So my first number is 3, but my second number is 6 minus that, and so my second number is also 3. So now find two numbers whose product is 16 and whose sum is a minimum. So we're going to set this up the same way. Our first number we'll call x. Our second number we'll call y. We're finding these two numbers. Their product is, okay, so x times y, that's the product, is 16. And the sum is a minimum. So x plus y is, we don't know. But the word minimum is there, which means I will be using calculus. So pick a variable that's the easiest to get alone. So again, I'm going to pick this y here as my easiest variable to get alone. And so y is 16 divided by x. substitute that into the other equation, x plus 16 over x equals the minimum. So now I'll bring calculus into that, and I'll do my math 8. Okay, again for my window, because my product is 16, that means things are multiplied to make 16. These numbers, aren't going to be super big. They're going to be probably less than 10. So you can set your window up to be 0 to 10. Okay, the graph here is a little bit of a different shape. It comes like this. But we're still looking for the minimum, so where it's crossing from negative to positive. And so we'll use our second trace to find the minimum. Make sure that you round to 3 decimals as necessary. But this turned out to be 4.000. So my first number, find the two numbers, my first number is 4. My second number should be 16 divided by that, which is also 4. So they both turned out to be the same thing, 4 and 4, the two numbers whose product is 16, whose sum is a minimum. Okay, let's move on to a little bit of geometry. So we want the distance between any 2 points. So let's draw any 2 points, x1 and y1, and we'll say we've got x2 and y2 up here, and we want to know what's the distance between them. Well, we do this by imagining a right triangle. And this right triangle would share the x-coordinate with the dot directly above it, and it would share the y-coordinate with the one directly to the side, so it's x2 comma y1. And so we want to know what's the base. And so remember, the base is the subtraction of the x-coordinates. So my base is x2 minus x1. That's the subtraction of the right x-coordinate minus the left x-coordinate. And then my height is the subtraction of the y-coordinate, so y2 minus y1. And so the distance between them is the Pythagorean theorem. A squared plus b squared equals the distance squared. So we're going to call that distance d. So if I say a squared plus b squared equals c squared, the a is the base, x2 minus x1 quantity squared. The b is the height, y2 minus y1 quantity squared, and the c is the distance d squared. So if I want to get d by itself, I'll apply a big square root to both sides, and the square root will cover the whole thing. x2 minus x1 quantity squared plus y2 minus y1 quantity squared. The square root does not cancel out the squares because it's an addition problem. And so my distance over here is now the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Okay, that's all geometry. So then the question is, how do we minimize this distance? We do that by how we minimize anything, by optimizing using calculus. And our calculus is either a derivative or a math 8 on your calculators. So let's actually do a question. Find the point P on the line 1 minus 2x closest to the origin. Okay, closest to the origin. All right, well, let's get a visual of what we're looking at here. Okay, here's the origin, 0, 0. The line 1 minus 2x is a line that starts up here and comes down. So what point on here, where would there be a point P? And point P is going to be x1, y1, where the distance between them is closest. So when you have a closest distance, that means minimum. Okay, well, we want to think about the right triangle that's formed here and the distance between these two things. Okay, we want the distance d. Well, we know that the distance is the equation, the square root of x2 minus x1. These are my x coordinates, minus 0. And you know, since I only have one x, I really don't think I need to call it x1 anymore. I'm just going to call it just x. So we'll just call it x today. Okay, squared plus, and the same thing with y. There's only one y, and the other one is the origin, so I'm going to erase the 1 there. So we just have x and y is fine. So then we've got y minus 0, quantity squared. But what is y? Okay, remember that y is 1 minus 2x. So I'm going to replace y with that expression. So my d becomes the square root of x minus 0, so that's x squared, plus y, which is 1 minus 2x minus 0 squared. So there's my equation for the distance. Square root of x squared plus the quantity 1 minus 2x, quantity squared. Remember, the square roots do not cancel out the squares. But now I want to find the minimum. So I'm going to do math 8 on this expression. Put it in your calculator. Find a good window. Now remember, your window, we're talking about 1 minus 2x as an equation, and this is going to hit here at 0.5, so your window is going to be really small. It is not going to be one of these big windows. It's going to be a small window. So I think you're going to be good in setting your window as 0 to 1, and that's going to be fine. And when you graph this on 0 to 1, you're going to get a graph that looks like this. You should do that on your calculator just to make sure. And this is your minimum value here. So then you'll find that minimum value. Make sure you round to 3 decimal places. And that turns out to be 0.4. Now that doesn't quite answer the question. Okay, we need the point P. So we have our x for point P, but we don't have the y. So you're going to have to plug that back in to y. Where is that? Well, that's right here. So you're going to plug that back in, and you're going to get 0.2. So those are the coordinates of the point P on this line that's closest to the origin. All the other points, whether they're to the left or the right, are all farther away than that point. So we can come and just adjust our drawing and say that this point we just found is 0.4, comma 0.2. That's its position. All right, let's try another one. Find the point P of the function y equals square root of x closest to the point 3, 0. All right, so let's get our square root, and we all know square roots look like this. The 0.30 will be sitting right here, okay, 3, 0. And then we want some other point P on the curve somewhere. Let's say maybe here. And that is x, y, who is the closest to the point. So the stuff between them is the minimum. Okay, well, how do we find the closest distance? So d equals the square root of, all right, we need the equation. So I'm going to do the two x values. So that's 3 minus x, quantity squared. And then the two y values, the taller y value is y minus 0, quantity squared. But what can I replace y with? I can replace y with the square root of x. So d is the square root of the quantity 3 minus x squared plus the square root of x minus 0, quantity squared. And that is what I want to do my minimum to. So there I'm going to do my math 8 again to that expression. Okay, now thinking about my window, look at where your x coordinate is. Your x coordinate is 3. So your window is going to, not be, again, a huge window. It's not going to be 10 or 20. It's going to be something small. I would just say, why don't you just go 0 to 5, and that should be a good visual for you for your window. By the way, for all of these, I've been pretty much keeping a negative 10 to 10 for my y. All right, again, so I'm going to see this one. It's going to be crossing like this. And I'm going for my minimum here. And that turns out to have an x value when I do my second trace of 2.5. But that's not the y value. Okay, that's for point P. I need a y value also, so I have to plug it back into the square root equation. So I want the square root of 2.5, which is 1.581. So now I know the coordinates of this mystery point over here, that this mystery point turned out to be 2.5 and 1.581. And that is the point that's closest to the 0.30. All the other points are to the left or to the right are all farther away. Okay, now let's talk about some business problems, some economics problems. In economics, we define profit as being the difference or the subtraction between revenue and cost. Okay, in economics, revenue is incoming money, incoming dollars, and cost is outgoing dollars. It's not the cost to the company, it's the cost to the boss, to the employer. He's got to pay his workers, he's got to pay for materials, he's got to pay his insurance. So the profit is the difference between them. So it's incoming minus outgoing. All right, so suppose the revenue function, the incoming money, is 9x, and the cost function, the outgoing money, is x cubed minus 6x squared plus 15x, where x represents thousands of things that are being made. Is there a production level that maximizes profit? And if so, what is it? Okay, well, we want to come up with a profit. So P of x is the R of x equation minus the C of x equation. So profit equals 9x minus parentheses x cubed minus 6x squared plus 15x, which is a little distributing of the negative for me. So that will give me 9x minus x cubed plus 6x squared minus 15x. And if I combine like terms and put everything in the right order, The negative x cubed comes first, the 6x squared comes next, and then 6x is the combined like terms. That is the profit equation. Haven't used any calculus yet, but I'm ready because I want to maximize the profit. That's the key word that tells you you need to do some calculus. Now this one's not so hard to do without a calculator because I can do the derivative. So you could either do the derivative by hand and find a p prime, which would be negative 3x squared plus 12x minus 6. And you could set that equal to 0 and you can solve it. Or you can graph a math 8 and you want to make sure to pick the maximum this time. Now you might be thinking, why don't I just do math 8 all the time? Well, it depends on how good you are at finding windows. If you feel like you're good at finding windows, then yeah, I would say for sure go with math 8. If you feel like you struggle finding windows and you spend all your time trying to mess with and find with a good window, well then do it by hand. Use the quadratic formula and you'll have the solution and you don't have to mess with finding a window. It's totally up to you how you want to do that, okay? So totally you could use a quadratic formula here. X equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And you would have the answer. Or you can graph a math 8. If you graph a math 8, please tell me what window you decided to use. Okay, I'm going to use 0 to 10. My graph looks like this. I have 2 answers. I want to pick the one that would guarantee me to be the max. So that's going to be the one that's crossing from positive to negative. So either way, quadratic formula or math 8 graph, it's up to you. We end up with 3.414. That is the production level, but remember that X represents thousands of units. So your final answer should be multiplied by 1,000. So 3,414 units should be made. Okay, now who knows what you're making? Okay, are you making sweatshirts? Are you making phone cases? Like, what are you making? But whatever you're making of, this company should make 3,414. All right, let's see. I think these are the same slides duplicated, so we don't need to do it again. Okay, we're done. All right, so I hope that that's helpful to you in getting you started on using calculus in situations in distance, geometry, and economics. All right, I'll see you on Wednesday.